Hi, how's it going? Andrew here from Get Into Game Dev. In the previous exciting episode of this series, we got a ray tracer going, and it had a single sphere. And that's not it. And it had a single sphere. But the issue is, the data that we had to represent the sphere and the camera, that was hard-coded into the shader. And we really don't want to do this, right? So we're going to have to do a little bit of work before we get this up and running. To start with, we're going to make classes for the camera and the sphere, okay? And then we're going to have a class for the scene, and the scene will describe the camera and a bunch of spheres, and we'll pass all that data in. Okay, so I'm actually going to copy paste this. Why not? So here's our camera class. We import all of our NumPy and OpenGL stuff and all that. We might need that. We have this camera class, okay, and all we need to do to define a camera is set its position. It's going to have two angles. Theta is the angle around the z-axis, so like the horizontal flat on the ground, left to right angle, and phi is like polar coordinates, the altitude, the angle around the y-axis. Okay, then we have this function here which sets up the fundamental vectors, forwards, right, and up. And we're going to need pyr or peer. So we'll just go to config and we'll go import that. That's a pip install if we don't have it, but that should be fine for us. Good. So first of all, what I'm doing is I calculate the forwards vector based on spherical coordinates. Go look up spherical coordinates. Actually, you know what? I'll insert that. I'll do some math. I'll insert that in here. Usually, we're used to polar coordinates being polar coordinates. So we have our x and y axis, and we can look around any angle we want here. Let's call this angle theta. In this case, our forwards x coordinate would be, we'll go cos theta, and our forward y coordinate would be sine theta. And our forward z coordinate would just be 0. We'd be looking flat along the axis. What I'm doing now is I'm also introducing vertical angle called phi, is what I like to call it. And I'm not quite going with the standard convention, measuring phi away from the z-axis. That would make sense. But I think of phi as like a variation away from the horizontal. So positive is up and negative would be downwards. And then if we look here, okay, so in the horizontal, now this horizontal is, the hypotenuse is this side here, which has a length of cos phi, and the vertical has a length of sine phi. It's a little dodgy, but here's how it goes. We have cos theta times cos phi, sine theta times the radius on the horizontal, which is cos phi, and fz is just sine phi. So that's how we describe a general forward vector in spherical coordinates. The other thing is the idea of getting like let's say we have our camera here. It's looking kind of, so if we go like this, it's looking kind of up a little bit. Okay. And we have our forward vector, but we want to get our left and right. So, our right and our up. So the first thing we do is we get our right vector. And the way we do that is we don't have an up vector, right? Because the camera is tilted a little bit, but we have an idea of like a global up vector, which is Z. Provided the camera is never looking directly up the Z, this should work, which we can constrain that. So in order to get the right vector, we imagine, oh, light went out, ran out of battery. Okay. So what was I thinking? This global up and this forward make kind of a plane, and we want a vector which is orthogonal to both of those. So we, by the right-hand rule, would be forwards cross z. So we take the forwards vector, cross the z vector. That produces the right vector. Okay. Then we want to get the camera's actual like up vector, which might be tilted a bit based on the camera's tilting. Well, this up vector is perpendicular to both the right and the forward. So by the right-hand rule, we go right cross forwards, and our thumb is going up with that up vector. So it's right cross forwards produces our up vector. Something like that. So that's the basic idea of what we're doing here in this code. Okay. So we're using the standard method to get the right angle and the up angle based on the vector cross product. All right. Then we're going to create a sphere class. Okay, fair enough. And here it is, very straightforward. We define the center of the sphere, the radius, and the color. And yeah, we store those. So what we're doing is we're going to be reading these properties. Awesome. Now we're going to make a class for our scene. And here it is. I know I'm rushing this part, but here we go. So we import all of our standard imports. Our scene is going to describe spheres and cameras, so we import those. Then we create the camera as a single object, and the spheres is going to be a list of spheres. So here I'm creating 32 spheres. They all have random positions and attributes and everything, but I have set it up so that they are all like in front of the camera. Awesome. Okay, so now let's get to the meat and bones of it, and that is our rendering function. So let's go to our app. First of all, we need to import the scene, and then where are we? We've got our graphics engine. We're also going to create a scene. Okay, and when we render, so just created that there, when we render the scene, we're going to pass our scene in as an argument so that the engine reads all the data in the scene and renders that all. Awesome. Okay, so now we go to, well, let's go to our shader for a bit. So we have this ray tracer, and we've got these sphere and everything set up. Awesome. So now, at this point, I'm going to do everything with uniforms. So we're going to have uniform for our camera and a uniform for our set of spheres. And I'm going to set that up as an array of 32 spheres. And just in case, for future proofing, we might want to be able to pass in a number of spheres. So if we don't want to render a full 32 spheres, we can only render, the first 2 spheres or something, just as it goes. Now, I know it's a little strange passing in a float for something which should be an integer. I tried a few times. I just couldn't get the integer thing to work. Float works fine as an upper bound, so that's okay. Okay, so now instead of all of this stuff, we can just get rid of that. And we can get rid of this sphere thing as well. So first thing we do is we set up our ray, And the camera is being set up in that all of that data is coming through in the uniform, so we're just reading that off. So we'll read the forwards, right, up, and position from the uniform camera viewer, which we'll pass through in a second. Then we can get rid of all of this. And okay. So what I want to make a function which takes the ray that we've just created and shoots it out into the scene and returns which color that pixel should be based on that ray. So first of all, I'm just going to declare all of this up above. Okay, so we'll have our prototypes up here. So we'll have a function which returns a three-dimensional vector called ray color. That takes a ray. And there's something else. So we're going to have multiple rays. So what I'm going to do is I'll create this in a second. I'm going to make a struct called a render state. And a render state keeps track of which information we get from a ray hitting something. So what do we need to know? We need to know how far the ray has traveled to hit something so that we can keep looping through all of the spheres and pick the closest hit. We also need to know basically which color the ray hit. So we'll call this, yeah, why not? Now I'll just call this hit. Okay. So this function will take a ray and test it against a sphere. And it will also have a minimum and maximum range for t. So the larger t is, the further that point is away from the camera. We can use this to restrict the hit. So putting a minimum t is probably a good idea. And putting a maximum t will just help us to make sure that we're only getting the closest sphere. Why can I not say sphere? It's been a long day. Okay, so what else do we need? We also need to take in a render state. Okay, so we have probably deferred this as long as we can. Let's create the render state struct. We'll be adding to this later, but for the moment, again, all we really need is to track how far the ray traveled, the color it hit, and I'll put a Boolean thing in here. And the reason for that is that we want to check whether we actually hit anything. Okay. So we could take this hit function and have it return a Boolean. However, it returns a render state because we want to store all that information for that hit, or possibly not a hit. So for that reason, we take in a render state, we update it, and we pass it out, including whether it hit something. Okay, so now let's have a look at the ray color function. Okay, so this is our basic ray coloring function. Important thing is for the minimum t, we put in this number because it's a good idea just to truncate it so we have like a near distance so we don't get closer than. And for the furthest distance, we pass in nearest hit, which is updated on a hit. So in other words, we keep progressively restricting our maximum ray length so that we're only ending up with the closest sphere. Awesome. Let's have a look at the hit function. I'm just going to copy this in. Okay, so we have this function declared as above. First of all, we do our standard test that we did from the video in the series, previous video. If discriminant is bigger than 0, then the quadratic formula has a solution. In this case, we actually want the solution. Now, with the quadratic formula, there are two branches. It's plus or minus square root of the discriminant. However, minus square root of the discriminant will give us the closer piece, which is what we want. So we go with that one. And then we check our t. Remember what I keep saying, putting a conditional like this in a shader does absolutely nothing to optimize the code. It just selects for the correct sort of thing. So if our t is within our acceptable range, then we grab that data, update the render state, and yeah. Alrighty. Cool. So that is all set up. Our shader is good to go. What we need to do now, our shader is good to go, provided I haven't made any mistakes, which would not, it could happen. It could certainly happen. Next thing we need to do is set up our engine so that we are passing in the data. For one thing, down below, we need to make sure we're taking in a scene object. Now what do? We use program, and let's make a function called, I don't know, prepare scene or something, prepare shader, something like that. So what we want to do is we want to pass in the scene, run through the scene, grab the data, send that off. Okay, so let's create that. Okay, I think that's working. So, I mean, this code should be pretty self-explanatory if we've done OpenGL and uniforms and stuff before. We're just passing through the camera attributes and the number of spheres that we're working with, and then we're looping through the spheres and passing that in. I used an underscore here because I have a module called sphere, and I know that I'm not importing. I know that I'm not going import sphere up here, but it's good practice because getting into the habit just helps me, keeps me from making bad mistakes. Same thing with this use program. Even though I've already declared it down here, I am super superstitious about always declaring a shader when I access it. Because if you, as you may know, OpenGL does not give us any errors here. It just fails without an error. Okay. So let's just see if this works. Okay. at line 38. Unexpected something. I probably forgot to... Oh? Okay. Ah, right. Okay. Maybe this is it. I forgot to specify the data types for these. They are both floats. Let's give that a shot. There we have it. Okay, so see, we've got multiple spheres in the scene. Quite a lot of them, 32. But there's an issue with this. Clearly, passing data in this way is not optimal. I mean, devices have limits. I think if I pop this up to... I don't have to pop it up too much. Let's say we want to pass in 64 spheres. To be honest, if we're making something, passing in 64 objects shouldn't be... Okay, it handles that. Well, the other day it wasn't handling it. What's going on here? Okay, let me just push this to the max, okay? Let's say we want to pass in 1,024 spheres. Please fail. Yes, it fails. So there's a limit, okay? We can only pass in so much data through uniforms. So the question is, what is a more mature, more robust way to pass in data? Well, there are two options. One option is to create a texture and load the image into the pixels of the texture. And the other option is something called SSBOs, shader storage buffer objects. I played around with SSBOs. I found them a little bit finicky, especially for Python, and the reward wasn't quite there. The benefit of SSBOs is they are just simply limited to how much space you have on your graphics card. So you can pass in heaps of data, almost unlimited. But I'm going to go with images. I find that passing in images is the right combination of flexibility, ease of use, and still does more than enough. Let's look at images. Now, what are we going to do here? We'll keep all of this, except for this buffer of spheres. Instead, we will declare an image, and it's pretty similar to what we had here, right? Except we're going to set this to binding number 1. And we also need to specify that it's read-only. By default, the shader likes to have like kind of one output. But anyway, well, I haven't played around with that too much. Let's just set this as read-only, and we're going to call this spheres. Okay. Okay, I'm going to leave that there. I'll come back to it. Now let's go to the engine. And probably clear this off for now, because we're not doing uniform stuff, but we will be using that. Okay, so just under create color buffer, I'm going to make create resource memory. Okay, so the thing is, what data do we need to pass in for a sphere? We need the center, radius, and the color. The center has X, Y, Z. The radius is just a radius. And the color has red, green, blue components. Now, each of these is a 32-bit float, or can be represented as such. Now, the image format that we're using is RGB32F, which means each of these channels is a 32-bit float, and there's 4 channels, RGBA. So what we'll do is we'll pack the first 4 of these attributes into 1 pixel. Then we'll have another 3 attributes, and then we'll have kind of an empty pixel. It's okay. Now let's go about creating that. So it's a little funky, right, doing this, but what we'll do is we'll say for I in range 1024, we're going to create space for 1024 spheres, since that was what broke it before. And then each of those spheres is going to be taking up 8 numbers worth of data. Now I know the last numbers unused, that's okay. And I'll create a list, just blank for now. And just append an empty number there. So we're allocating space, empty space. Okay, good. So we've allocated all that space. We've turned it into a NumPy array, which is what OpenGL likes. Now we're going to create a texture to ship that data to. Yeah, why not? Okay, cool. So we've created that, we've bound it. We bind it to texture unit 1 because it is binding number 1. And then we'll just put in these. I hate it, but remember, really important, we need to be using nearest filtering because basically we don't have any sampling. We're just accessing the raw texture data. Then the last thing we need is we need to link that up with our data. Okay, good. So we send that over. So here's the thing. We have created a big, long list. It has 8 times 1024 elements just in a flat line. But we are telling OpenGL to interpret that flat line as a texture, an image, which is 2 pixels long and 1024 pixels deep. So it kind of packs that data together into that 2-dimensional image. Awesome. So again, super important. The sphere that we're looking at is along the y-axis of the texture, starting at 0 and going down for each new sphere. And as we go across in the x, we're grabbing the different attributes, and they are packed in this order. X, Y, Z of the center, the radius, and then the second number is just the red, green, blue of the sphere. Awesome. Okay, so we've also stored this persistently because we're going to be updating it every frame. Cool. So now we'll need to basically do that. Now, I'm going to create a separate function to record sphere data. And yeah, as I write this, I do realize that I could use slicing operations and make this a little bit more efficient, but that's okay. Oh, geez, I probably should do that. We'll look at it. We'll look at it later. So remember, we have this, but even though it's been interpreted as a 2-dimensional image, we've really kind of got like x1, y1, z1. Okay, so there's like 8 numbers there, and then the next 8 numbers are for the second sphere, so it's x2, y2, z2, continuing on for another 8 numbers. So we've got a flat representation in memory, and we need to account for that. That's why we've got 8 times I. So the center of the first sphere is number 0, and then there's 8 numbers, so it goes 0 to 7. So the center of the next sphere starts at number 8. I hope that makes sense. Basically, we're just accounting for the flat layout in memory. Okay, so hopefully this is looking okay. Again, we have got 8 positions that we could fill. We're only using 7 of them. So instead of going 0 to 7, we're just going 0 to 6. Okay, awesome. So we've got that set up. Now we can use that because we can go self record sphere, sphere number I, passing in that one. Okay, cool. So then what we need to do is we have updated our buffer. We need to update the underlying texture. Okay, so we activate texture index 1, texture unit 1. We bind that in. Then we copy over the memory. So copy over that whole texture. And then we grab binding number 1, set that, match the texture to binding number 1, put it into read-only mode, and yeah, we should be good. We should be good. Okay. And we could make this more efficient, so we could have like a test to see if a scene becomes out of date and needs to be updated, and not update every frame. That's a great idea. But yeah. What am I saying? Let's just try it. Of course, right? I wasn't finished here. So we've got this sphere texture, but then we need to access that sphere texture. So we'll make a function which returns a sphere, and it gets it by unpacking the texture. Okay, so what I do is I tell the program, okay, I want this sphere, get it for me, and it unpacks it from the texture. So we'll go unpack sphere I. Okay, awesome. Okay. So we create a sphere, then we're going to grab the data for it and chuck that in there. So what this does, it takes the texture that we're reading from and an integer vector being the position to read from. So we want to grab the first pixel in the X, and the Y will be the index. So again, that starts from 0 and it goes on and on. First time we load that, that gives us the center and the radius. Then we're going to load it again to get the color. And that'll be pixel index 1 across. All right, so get the first 3 attributes, X, Y, Z, and then get the 4th attribute, W. Oh, yeah, what am I doing? X, Y, Z. Okay, so we've got it. All right, let's try that. What are you doing? Oh, typing too quickly. I don't think I'm a fast typer, but somehow I always type too quickly. Right, engine object has no attribute sphere data. Yes, of course it doesn't, because I forgot to call that function. So we create a color buffer, then we create our resource memory. Third time's the charm. Did I forget to write self? No. Self sphere data. So what have I messed up? Oh yeah. Of course. The first time we read it in as a basic list, and then, yeah. And there's no reason to do it one way or the other. We could just overwrite that. We do it once at creation. But there we have it. Wow. Okay, cool. So, benefits and drawbacks. Clearly, it works. It's stable. We could pass in 1,024 spheres. Passing in that texture every frame does... It is a performance hit, okay? So probably not necessary to go this far into it. If, for instance, we go back to our engine and we change this to just 32 pixels, so 32 spheres, then I want to imagine it'll go a little bit faster. Let's give this a shot. About the same speed. That's fine. That's fine. Okay. So cool. So there it is. We can now pass data into our scene. Have you ever wondered why ray traced scenes have just 1 or 2 spheres and they look very nice? It's because passing in lots of spheres slows things down. There are things like acceleration structures we could look at. We're not going to do that for now. All right. So I hope you had fun. Good little coding session. And I'll see you in the next one. Bye.